Hi, I'm Mark Weitzman. Let's use what we used in the last problem to do some typical problems. So here's a problem. A pion, we usually use that symbol. Its mass, or m pi, is equal to 273 times the mass of the electron, and the mass of the electron is 0.511 MeV. And so the pion decays into a muon, and the mass of a muon is 207 Me, and a neutrino, muon plus a neutrino, and you should know the mass of neutrino is 0, at least back then it was. Nowadays we actually believe that neutrinos have some finite rest masses, but they're really small, so we can ignore them. And we want the kinetic energy and momentum of the muon and the neutrino. So we have those formulas, and we're just going to plug it in. So the kinetic energy of the muon is equal to 273 Me minus 207 Me squared divided by 2 times 273 Me, and this works out to 4.0768 MeV. Okay. And then we can do the kinetic energy of the neutrino, and this is going to be the same thing basically. Notice that in that formula over there, the rest mass of the neutrino was 0, so that's why we didn't have a term here. And here we're going to have 273 Me squared minus 207 Me squared divided by 2 times 273 Me, and this is equal to 29.65 MeV. Now, since the kinetic energy of the neutrino, since there's no rest mass, that's just the energy of the neutrino, so the momentum of the neutrino is also 29.65 MeV. Maybe we should technically go /C, but we're always working with C equal 1. And then the momentum of the neutrino, of the muon, since there's in the rest frame, the total momentum is 0, so this is going to have the same momentum in the opposite direction as the neutrino. So this is also going to be 26.65 MeV over C. And that's it for this decay. So using those formulas, you can solve a lot of these problems. I'm going to do one more. So let's say we have an excited atom of mass m star, so that represents an atom, and it decays into, it ends up having a mass of m minus del E. It emits a gamma ray, a photon, so we have that, and then we have squiggly lines are usually photons, and E gamma. So this is our before and our after, and so in a sense we're taking into account the recoil of the atom when it emits the photon. We want to calculate the energy E gamma of the photon. So again, just to, in this case we would have m equals m, m1 equals m minus del E, and m2 equals 0 because the photon is massless. So substituting in those formulas, we would get E gamma, which is equal to T gamma because there's no rest mass for a photon. That's just m squared minus m minus del E squared over 2m, which is equal to, when you simplify it, del E 1 minus del E over 2m. Okay, so these are just a couple of simple decays. In the next video, I'm going to do something with producing particles at threshold, and it's using basically the same principles, and we'll compare 3 of them to understand how accelerators produce particles. Thank you very much.